this video, we're going to see how you can optimize the hyperparameters in your modeling efforts. We'll start with optimize parameters grid. Okay, so we left off doing some cross-validation, which is inside this. So here's the cross-validation we did before. And I've got a decision tree, and I can set the parameters on my decision tree. I can apply my model performance to data just like I have before. Now what I'm going to add is in modeling, if we go to the optimization folder here and choose the parameters, I've got the optimize parameters grid. So what I've done is I dragged that in here. And then I took the cross-validation that was there before and just put it inside and then connected my ports. So now when we take a look at this grid, I have some options here. I can tell it how to handle any errors that it may encounter. And I can also tell it to log the performance and log all criteria that take place within this optimization run. Now, logging is a good thing to do because you will be able to see each individual result of each iteration of the optimization run. By default, it just reports your best results. And then at that point, you would have to then go out to your model and set those parameters accordingly. So the grid runs for everything. It tells you what the best thing is, but it doesn't necessarily leave your model at those best settings. So we'll get to that after we run this. Okay, so optimize parameters. And as I look here, I've got these selections on, and then I can go into my parameter settings. Now here, I'm going to go ahead and clear everything. Here you can see everything that is inside that sub-process. So I've got my cross-validation. I've got the decision tree. This would be the one, whatever your algorithm is the one that you're probably most interested in doing, although you may decide to do different feature selection criteria as well. All right, so performance. Okay, so let's take a look at decision tree. So under decision tree, I've got a number of different criteria that I can set. Do I want to run it with gain ratio, information gain, Gini index, accuracy, least squared? All right, so we can try a few of those. And look, it tells me right now I've got one parameter. I've got three settings, so I've got basically three combinations of parameter optimizations that I can run. All right, let's take a look at the next one, maximal depth. Now, if I look here, it says minimum of -1, max of 100 with steps of 10. So it basically is going to increment by 10 depth. Now that might be a little bit large, but you can see now I've got 33 parameters set. So let's say the minimum depth of our tree, let's say 2 levels deep, and max it out at 15. And let's say the number of steps would be 14. All right. And I could also change the scale to be, it by default is a linear scale, but I could change it to be quadratic or logarithmic. Okay. So now I've got 42 combinations because I made a change. I can also, let's see, apply pre-pruning. Okay, that's a true or false. So now I've doubled my combination. So you can see every time I add a new parameter in here and allow it to, the grid to work with it, the number of iterations of optimization testing I'm going to run increases. Add another one, the minimal decision tree size for the split. Okay, so minimum size for the split 1 up to, well, let's make that 2 to split a node. Minimal size, maximum size, let's make that 20 with, yeah, we could still do 2 steps, 10 steps in between. All right. So now I've got 924 combinations. Now, if I want to say, well, what's the minimum size I want one of my leaves to be? Again, this is an overfitting criterion. So maybe I could say, well, I could try it out with 1 leaf, but let's say the max would be 5, which gives me 5 steps. All right, so 4,620 combinations. We could set, well, what is the minimal gain that I want to see before I stop? And I could set the minimum to 0. I can leave it to infinity. And you can see now I've got 50,000 combinations. Well, let's say I wanted to make 100 there. All right, so now I've got 466,000 combinations that's going to go through. As you can see, it's a good idea to be judicious as you work your way through here and add criteria and determine what values you want to allow your criteria to hold. All right, so now if I click OK, and what I've done is I took the automated feature engineering we did earlier, and I just took that feature set and saved it in my repository here. So it's called Bike Buyers Feature Selection. And I just brought that in here so that I could not have to run this every single time I run the model going forward. All right, so I'm doing my typical processing. I'll apply this feature set. Now I'm going to optimize parameters, running those 466,000 combinations. Now that is a large number of iterations, and this would certainly be something that I'd be comfortable maybe running overnight or during my lunch hour. But let's say for my minimal gain that I want to have, minimal gain of 0, max of 0.5, okay, with 5 steps. All right, so now I'm down to 27,720 combinations. I'll go ahead and run that. So I'll click OK, we'll run that. And we'll see what we get. As the process runs, you can see I've got a little timer down here that tells me how long everything has been running, how much the optimized parameters operator, which it's working on right now, has been running. And here's how many iterations it's gone through in that optimized parameters so far. All right. So we'll go ahead, we're getting closer. We'll go ahead and you can see we're 65%, 66% of the way done, 67. So we'll pause the video and come back when it's done. Okay, we ran in just a little over 4 minutes, and we can see the feature set results. The cross-validation. So this is the results of the cross-validation, the last cross-validation run. Here is the decision tree that was created from the last model. Here is my performance, accuracy of 69.2%, AUC 0.759, precision and recall I also grabbed as measures, performance measures, and an F measure of 66.08. Okay. So now I can see the parameter set that optimized parameters comes back with. Here's my performance, AUC, recall, F measure. The decision tree criterion was JITI index, maximal depth of 10, pre-pruning true, minimal size for split 13, minimal leaf size 3, and minimal gain 0. All right, now I also have my grid, my optimized parameters grid, and I can see all 27,720 iterations of this run in this table here. And I can see which criteria were used. So here is the split criterion used. Maximum depth of that particular tree. Was pre-pruning used, true or false? Minimal size for split. Minimal leaf size. Minimal gain. And then I can see my performance metrics. What was the accuracy of that run, the AUC, precision recall, F measure. And if I want, then I can go ahead and sort to see, well, which one gave me the biggest AUCs. I've got, looks like 6 models. Which one gave me the most accuracy? I've got, looks like quite a few that came in at 0.717. Yeah, quite a few pages there, and then 716. What about F measure? Okay, so in this case, sometimes if I have a 0 in the denominator of my F measure, I'm going to get something like that. And then above that, .690. Precision, 0.734. So here you can see I get some of my higher precisions and recalls and F measures with the higher AUCs as well. All right, so this gives you some information, and then you can check these settings. So now let's say I wanted to go with my top AUC, and all of these look like they have the exact same metrics just about across the board. So I could then say, well, I want to set my decision tree to decision tree. Let's see how we can do that in our process. So now I can go in and I'm going to copy this. And I will, let's see, I need another multiply now. Okay, so now let's say maximal depth 15. Pre-pruning false. Minimal size for split 20. Because it was false, none of that really mattered. Minimal leaf size. Minimal gain. And the criterion was gain ratio. Minimal gain of 0.5. All right, so now let's go ahead and run this by itself, and we've got our model. And then we can run this cross-validation with this data. and these parameters, and now see how our model performs and use the confusion matrix to help us in our work. All right, so that is the grid approach to optimizing parameters. Now, as you can see, the more options we started to consider, the bigger that grid became, exponentially so, as we added more hyperparameters. And the hyperparameters are going to vary depending on which algorithm you're using. So if you use other algorithms, you're going to have different hyperparameters to modify, and therefore you're going to have different choices to make in your optimized parameters grid. All right, so that means you're going to be basically adjusting these a little bit for each of your modeling algorithms that you're using. All right, let's take a look at the other one. So another approach to optimizing parameters is an evolutionary approach. This one is going to try and get better every time. The grid one just sort of walked us through every possible combination that we had set it up and told it to do. Evolutionary, you set some parameters for it, you tell it which parameters to dig into, and then it works to try and find better values for each of those parameters, trying to come up with an optimal solution by stepping its way toward better performance, depending on your performance setup. All right, so there is the possible limitation that you will miss out because it's looking for maybe a local solution. So the grid one is maybe a better way if you have the time and the resources. Every single combination of parameter settings to really fine-tune and squeeze the last bit of performance out of your model. Evolutionaries might be a good place to start. And again, just like we saw before, we'll edit our parameter settings. So if we are in our decision tree, well, what's the maximal depth of that decision tree? Here, I can set a min and a max, but I don't set the number of steps. So I can say, I can do my 2 through 25 again. But then the evolutionary approach is going to work its way through and trying to get better with them. Minimal gain. If I bring that in, I could set a min and a max value. My confidence levels, min and max values. Minimal leaf size, min and max values. And so on down the line. Size for split and number of pre-pruning alternatives. Now you'll notice that one thing that didn't show up was the split criterion. So this is something you'll have to do manually to work your way through. Another thing to keep in mind. All right, so we can run the evolutionary approach, and then we can maximize the number of generations that it will work its way through. The default is 50. Early stopping if it starts to come up to a local optimal. You can also tell it to stop if it gets stuck and doesn't find anything better after a couple generations. A generation is more or less the evolutionary's equivalent to one of the iterations that we saw in the grid approach. All right, keep the best. And then you've got other types of parameters that you can set, which mutation type, which approach is the default is a tournament, but you can select a number of other alternatives. And then, of course, your local random seed. All right. So now when we run the evolutionary approach for optimizing our parameters, And we did more or less the same thing. We did cross-validation, brought everything in. Let's run that one. Okay, so I optimized my parameters here. And you can see my maximal depth is 6, minimal gain infinity, confidence 0.01336, etc. Minimal leaf size 91, minimal size for split 3, number of pre-pruning alternatives 6. And then I also have my 440 rows of data where it gave me all these different values along with my accuracy, AUC, F measure, precision, and recall. Okay, so you'll want to change the settings and try maybe a different approach. Maybe another approach will give you better results. But you can see the optimized parameter does tend to run a little bit quicker using the evolutionary approach than the grid approach. All right, so that's parameter optimization. Let's get back and see what you'd like to do next.